Hola, welcome to the first Lambda World Meetup. Thank you for this supernatural applause. Thank you for coming. Thank you for coming, the people that is watching on by streaming or watching the recording afterward. For why Lambda World Meetup? Because many people around in many different communities were asking for Lambda World. When is gonna come Lambda World again, and so on. The answer we don't really know yet, but we are in the need to come together and to talk about the technologies that we love, the technology that we can find in Lambda World, the formal verification, functional programming, all the different languages that we can find in different tracks in Lambda World. So this is the first test of a meetup. It's a nomad meetup. It's something that right now we are in the south of Spain, in the offices of 47 Degrees, soon to be Xivia Functional. And with the idea that to repeat this when we exactly don't know, but soon, where we don't exactly know, but in another good place, and surrounded of good people. So thank you for coming again. Thank you especially for coming from Madrid to Juan Serrano, our very first speaker and very, very good friend, founder of Habla Computing and also organizers of the Scala user group of Madrid. Thank you, Juanma. Please enjoy your talk and enjoy your time with Lambda World Meetup.
Well, thank you very much for inviting me to this very first Lambda World Meetup. With Raúl about possible topics for this talk, and I suggested Tagless-Final. He said something like, Pisha, my guys at 47 Xivia Functional are doing Tagless-Final every day. So I will assume some familiarity with the style. And I will focus in some particular questions that we found interesting while working with this style in different projects. Okay? And the first question is about the relationship between Tagless-Final and NTL, because there are times in which it seems to me that they are confused, but they are very, very different styles. Okay? So we have here some. Doesn't work? Yeah? No. Okay. These are two sample code fragments. On the top, we find the monad type class, monads, applicative, functor, foldable, traverse, and so forth. So forth are the basic building blocks for doing MTL. Okay. On the bottom, what we have is a fragment of the QL language. QL is a relational query language, which allow us to translate in a very efficient way sample queries which are programmed in an idiomatic style in Scala, okay, and translated very efficiently into SQL, okay, something like Quill, okay. And this is a sample of Tagless-Final, an exercise on Tagless-Final that can be found in this paper. One of the authors is Oleg Kirchaliov, which is the father of the style, of the Tagless-Final style. And we stumbled upon this code while working in a language in a query language, but not based on comprehensions, not a relational query language, but a language for writing queries, subqueries, using optics. And this was part of the thesis of Jesus. There are many similarities between these two code fragments. To start with, they are both type constructor classes, okay? Both the monad type class and the QL language are defined as type constructor classes. And also, if we squeeze a little bit, we find that there is a very strong relationship between the select and from method of the Coel language on the one hand, and the pure and flat map method of the monad type class. If, for instance, we remove df in this signature, what we find is more or less the same signature that we have in the flat map method, but with the df, instead of a generic f parameter, what we find is a list parameter. So there is some similarity, but they are not the same. And in order to explain the differences between both styles, what I think that it is useful is to consider the different roles that type constructor parameters may play. Okay? And in order to explain these differences, I will ask Chiquilicuatre for help. Chiquilicuatre, for those of you that do not know, was the Spanish representative in the Eurovision contest in 2008. Okay? And so, which are the three different roles that may be played by type constructor parameters? One, the breaking dance. Okay? Doing the breaking dance, everybody? Everybody doing the breaking dance? Well, that's nice. Okay. So the first use that we found of type constructor parameters is that the one that we see when using containers of information. For instance, a list of integers, a list of strings. Okay? If we have a list of strings, what we have is a data structure, a container of information, and the type constructor parameter A represents the type of information that we find in this container. Okay? We have a list, we can pattern match this list. If it is not empty, we will find an element of type A. Okay? Second, the cruzadito. Then we find different use of type constructor parameters, which is, for instance, in the state monad. The state monad is a computation, it's not a container. Okay? The state monad is a computation that when it is run, it will generate elements of type A. So the A, these type constructor parameters, do not represent the type of information that we find when we open the state monad. No, we won't find any A. What we will find is a function, it's a generator, a state transformation. Okay? It is only when this computation is run that we will obtain an element of type A. Okay? Third use, the Michael-Jackson. Okay? This use of type constructor parameters, the typical example that we find here is phantom types. There are type constructor parameters which are phantom types, okay? Which are neither the type of elements that we will find in our container of information, nor the type of information that we will obtain when the computation is run. Okay? This is something different. And these phantom types are useful in order to prevent or in order to get rid of ill-typed code. Okay? For instance, let's say that we have a list. If the list is empty, we cannot get the head of the list because there is no elements. With normal list, what we will have is a runtime exception. Okay? With this kind of safe list, what we will obtain is a compilation error, okay, which is different. How do we achieve this? Well, we achieve this simply by declaring an isEmpty type, which is an enumeration type. Okay? And there are two cases. Either the list is empty, yes or no. Okay? And the safe list declaration for the different cases, for the empty and cause variants, what it is declared is that for empty list, this type constructor parameter we have the type yes, and for the non-empty list, we will use no. Okay? Okay, and how do we use this? Well, when declaring a head operation, we can specify in the signature of the of the head function that the list, the type of list that we will receive for this function, the type constructor parameter is empty, has to be null. Okay? In such a way that if we pass an empty list, this type constructor parameter, the type will be yes, and the result will be what we have here. No, it's not possible. It doesn't compile. Okay? Okay, my claim is that in the QL signature, the type constructor parameters, the role that it plays is the phantom type. They are phantom types. Okay? They are not the type of the elements which are stored in this F or the type of elements that we will obtain when the computation is run, unlike in the monad type class. The monad type class will typically be instantiated with the same monad, with computations or with data structures, okay? And this F will be usually be a computation or a data structure. In such a way that if F is a computation, the flat map method, what does it do? The flat map method, which does is creating a new computation that will first run FA, a computation of type FA, and then a computation of type FB, which might depend on the result A of the previous computation. Okay? So we are sequencing imperatively computations. Okay? But in this case, in the QL signature, the F, it doesn't make sense that it can be interpreted with as a computation or data structure, because what we find here is, okay, what does it mean, this F? A computation that will return a list of A, and then it will execute a computation of type that will return a list of B, but what is received here is not an A, it's an F of A. It doesn't make sense to be interpreted as a computation or a data structure. But it does make sense to be interpreted as phantom types. Phantom types which allow us to constrain the kind of programs that we will write using this DSL. And it doesn't matter, actually, that this is an integer, boolean, or list. We might declare our signature using different tags. Instead of integer, we may use cheeky. Instead of boolean, we might use Michael, and instead of list, we might use a text constructor Jackson. Okay, and these tags make up the type system of the DSL that we are designing, that we are programming. Whereas the boolean, select, and from, okay, consists of the syntax of our language, the B and F rules of our language. Okay, and it doesn't matter which labels do we use for the type system. Of course, if we choose to use these awkward labels, the standard semantics of the language will be a little bit more complicated, because, of course, in our standard semantics, we want to use the boolean, the int, and the list standard types of Scala. Okay? But still, it can be possible. So, in general, the type system of a DSL, of a new DSL, is a very important piece of the design of our language. And in the case of the Tagless-Final style, it is explicit. Okay? It is explicit. In the case of the monad type class, no, it is not explicit. Okay? In the case of the monad type class, what we find is that, well, we have computation that we want to create imperatively sequencing these other two computations, but the type system itself is not explicit. Okay? Another difference that we find between these two code fragments, the QL language and the monad type class, refers to the way in which functions are represented. What we have in the flat map method is a continuation, a function from A to FB. Okay? And this has a problem for some interpretations, because we can't analyze the code that it is implemented in this function. We cannot do a static analysis, abstract interpretation of this. Why? Because in order to analyze the computation that we will run next, okay, we will need the value A. which is the result of the previous computation. Okay? So until the computation is not run, we won't be able to analyze this code. And there are sometimes that it is necessary to analyze this function, how it is made. Because, for instance, we want to make a pretty-printing of our program, we want to serialize our program, or we want to optimize the program, okay? In the case of the QL language, we do not have this problem. Why? Because here, in this function, we do not have A. We do not need a value of type A in order to analyze the code that will be generated by this function. We need a representation of elements of type A. And this is more or less the same as this other signature, where it is clear that we have is a representation of a function. And this representation of a function allows us to analyze how it's made, okay? How this function is structured in order to optimize, to rearrange different parts, and so forth. And, for instance, to implement this pretty printer. Okay? So we have this query. This is a query written with the QL language. Basically, what we have there is a query which obtains the different countries, and for each country we obtain the capital. We see if the capital exists and it has a population greater than 8 million. And if this is the case, then we return the name of the country and the name of the capital. Okay? We can obtain this interpretation, okay, which is a pretty printer. And we can't implement this interpreter using the monad text class. It is not possible. Okay? And there are other interpreters that we can implement. And this is basically because we do not have a monad instance for the constant factor. Okay? Any question? Any question in the chat? No? Okay, not so far. Okay. Second question. How do we optimize Tagless-Final programs? For instance, this is another example of an interpreter which demands complete access to the function, to the continuation function, okay, of the from method. This is an interpreter that what will allow us is to normalize this query. Because what we have here, okay, this pretty printer, it is clear, well, maybe it can't be seen clearly, but what we see here is that there are nested froms, okay? This is not standardized. And this, if we try to translate this query in a naive way to SQL, what we will have are subqueries, okay? And this is not ideal. Okay? So in order, as a previous step in the generation of SQL queries, what we need is to normalize this query. So there is a need of translating this query into something like this. Okay? And what we have here is we have from this table all countries, and then we obtain all the cities, and then there will be some conditions, and then we return something. This is the goal. And this goal can be obtained by using a special interpreter. Okay? A special interpreter that we call normalize, and which is parameterized by whichever interpretation, other interpretation. Okay? In this case, the string representation. So how can we write this normalized interpreter? This is what we are going to talk next. What we will do is following the implementation of this normalizer that we find in this paper by Alexis Leof, and that you can find in this talk that with much more detail, in this talk that we made for the Madrid Scala Meetup together with Juan Vázquez. Okay, and what we will do is just to give an overview of how these optimizers, these in normalizing interpreters are performed, the different strategies that they are. Okay, so our goal is the following: we have this unnormalized query, you see here that there is, okay, I will obtain for each country, and then for each city that meet these conditions, I will return a tuple of blah, 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 blah. Okay? And what we would like is to transform, to rearrange this query in such a way that it has this shape. Okay? First, all the tables, all the basic tables from our data model, and then a single where clause with all the conditions fused together with an end, and then a single select return. This is what we want to do. Okay? How do we do this? Okay. In general, what we have in a Tagless-Final interpreter is a bottom-up evaluation, okay, which starts from the leaves and goes all to the root. Okay? And this returning representation of a city, a representation of all cities, and so forth and so forth. And then we finally return a representation of a list of tuples, okay, which is what we have in this query. In order to implement an optimizer, in order to implement an interpreter which has to be able to somehow analyze certain parts of the tree structure, of the AST, of the abstract syntax tree of our query, of our program, what we need is to annotate the representations that are returned with the basic interpretation in order to identify whether we have to take a decision of renormalizing, of rearranging, or whatever. So, for instance, we analyze the all cities piece of information. What we do is returning not only a general representation of the city, but a table. We say, hey, this is a table. This is a basic table. And this is important. Why? Because we have to identify which representations are tables, because this has to be placed in the normalized query on the forefront. Okay? So all cities, the evaluation of all cities will return this table. Will return a representation of a city, but it will be tagged, it will be annotated with table. Okay? In the case of Boolean conditions, we do not need really to identify this representation specially. Okay? So this will be tagged with an unknown variant, okay, in our interpreter. Select, select, we had to identify that we have a select. Why? Because in the normalized query, we will have a single select, okay? And when we analyze a word, when we evaluate a word, we also have to identify that this is a word. And word and select will be part of a single annotation, okay? And for from, we also need to identify that what we are evaluating is a from, is a comprehension, okay? So our interpretation, the normalized representation, we have these variants, a noun, table, single, and comprehension, okay? So we will write an interpreter that will return, that will evaluate our expression using this data structure. Okay? In such a way that if we are evaluating a from, okay, and what we have is a comprehension in the left side, okay, which is already normalized, then what we have to do is to rearrange the information that is stored in this comprehension in order to fuse all these conditions that we have here in this first query with the comprehension that we obtain from right part. Okay? So this tree that we have here, whenever it is reevaluated and we will return a comprehension, it will be like this. Okay? And this part is already normalized. What we did is to fuse basically this where branch from here with this where. Okay? Nothing less, nothing more. Okay? And the evaluation proceeds bottom up until what we have is a complete normalization of our query. So, I mean, this is difficult without seeing any actual code, okay? But the important thing is this. We, instead of evaluating plainly all of our expression with the plain representation, okay, what we do is to annotate bottom up, okay, this basic representation with syntax. Okay, this is a comprehension, this is the table, this is a single, which means that it is a where clause together with a select clause, okay? And this is, these annotations are bottom up. And this is something that is called normalization by evaluation. When we are evaluating a Tagless-Final program in order to construct this kind of intermediate representation, okay, with comprehension and so forth, what we are doing is a kind of normalization that is called normalization by evaluation. And this is very nice. This is very nice because we can have in one shot, okay, in one shot, we can have all of our program normalized in one shot, del tirón. Okay, yeah.
So you're saying that this normalizers like adds a bottom up, so because the original representation of the program was expressed as a for comprehension, right? Is it possible that you in a for comprehension might be selecting multiple times the same piece of data? For example, select from user ID, whatever. Does this normalization process also take advantage to do things like batching, the duplication of IDs in terms of multiple calls? Or is it just like trying to reduce everything to a single?
It's a flattening, okay? It's simply a flattening of the different sub-comprehensions that you will find.
So
it is nothing less.
If there's two selects that need to be flattened into one, and the
two selects will be flattened into one, yeah.
And they're pointing both to the same query of data?
No, this interpreter will do that, but still you can do it. You can do it because you have access to all the expression, okay? There's no problem with that. But this will be an enriched normalizing that we might implement, okay, in a different, once the expression is normalized, and then you have all the information in, okay, in a single select, you might evaluate all the information that will be returned in order, if you can optimize a little bit this part, okay? But there are different aspects. Okay? And you can combine, okay, both optimizers. They can be written modularly. So what I would like to say about optimizing and normalization and so forth is that this bottom-up evaluation, this annotating representations in a bottom-up way, is something that do not always work. Okay? For instance, let's say that we have Boolean expressions, okay, and we have here is a false and true or false, annotated with a not, okay? And we want to apply the Morgan so that the not operator only affects the leaves, okay, of the tree. So the equivalent expression will be this, not false or not true and not false, okay? So how can we do this? Well, again, we can try this strategy, and if we have a what we want to do in this case, which parts, which kind of expressions do we want to identify in order to rearrange our expression? Well, what we want is that when we find a conjunction, if this conjunction is affected by a negation, okay, from the negation implementation, we need to know if what we are receiving bottom up is a conjunction. Why? Because if it is a conjunction, we want to eliminate this node. We have to convert this conjunction into a disjunction and push the negation down. Okay? So in our data structure, what we have are different cases. We have an unknown, we will always have an unknown, we have an and, we have an or. And this and or, the meaning is that, okay, we want to identify whether some representation is a representation of a conjunction of a disjunction. So a false, a true, or false, these are unknown pieces of information. I don't care. Okay? But when we have an AND, what we or, what we will return is an OR and it's an AND. And then, okay, when we have a NOT, what we will return is a unknown replacing this AND, okay, with an OR and pushing the negation NOT down. Okay? But what do we achieve with this transformation? Only one level down. Okay? Because this NOT has to be again pushed down. And we can, with this very same interpreter, we can obtain the full normalization by repeating the same normalization step. Okay? And combining these optimizers. But this is not optimal. This is not done in a single pass. In order to obtain this interpretation, this optimization with a single pass, what we can do is, instead of annotating bottom-up, annotating top-down. And for that, what we will use is something like the reader monad. Okay? And in this case, the interpretation will be a function from Boolean to representation. What does it mean, this Boolean? This Boolean means, are you in a negated context or not? Okay? This is the clue. And so our evaluation, bottom up, we will construct this function. Okay? And the evaluation of this function, what we'll do is the following. If we have the implementation of the literal, for example, literal Boolean, what do we do? If the context is true, it means that this expression is part of a negation. So what we will do, okay, is to replace the literal of B by not B. Okay? And if it is not part of a negation, the same. The same for no, for and, for not, and so forth. In the case of and, if we are in the context of a negation, okay, what we will do is to change and to replace and with or, and pass downstream true in this function, which means that you have to negate the next expression. Okay? So the evaluation will be something like that. For the whole expression, the annotation will be false. Okay? But when we find a not, we remove the not, but say downstream, okay, you have to be negated, whatever it is a conjunction, it will be transformed into an OR. And it is a basic atomic proposition, it will be negated and so forth. Okay? And this is in one shot, del tirón. But in this case, okay, the annotation flows top down. It doesn't flow bottom up. The evaluation of our expression is always bottom up. But we have to distinguish between the bottom up evaluation of a Tagless-Final expression, which is a catamorphism, which is a false, and this is always flowing bottom up, and the annotations. How do we annotate our expressions, okay? And how do we annotate information that will be used downstream? Okay? And these are like two strategies in order to implement these optimizers. Okay? One which can be related to the reader monad, and the other one that can be related to the writer monad. Okay? Another question. Some questions so far? A question in the YouTube channel? No? They are calm? Yeah? Okay, another question. Yeah.
We can infer the...
Wait.
It's not so important. No, is that we can just infer whether if it's not is top down, or top bottom, or bottom up, based on the signature itself. Whether if it comes from
the signature of
Boolean
this,
to the type class.
When we have a function, this information will flow top down. Yeah.
Okay. Yeah. What's that?
Yeah.
Thank you.
And with the annotation is flowing bottom up. Is that like the writer monad? In the writer monad, what you have is that you generate some information, but also together we generate another information, which is the annotation. Okay. Yeah. And the only thing is that in these evaluations, this it is only the notation that it is flowing up, because the original representation, okay, the non-annotated representation can be inferred from the annotation, okay? But it conceptually is something like the return monad. Another question that I find interesting, because it happens, we stumbled upon this question in some of our projects, is about the need of having values for our Tagless-Final programs, okay? For instance, this is a typical Tagless-Final program. This is in another language. This is a language for writing arithmetic expressions. And what we have there is an if-then-else constructor, okay? So what we have there is a very dumb expression. If 1 is greater than 2, then return true, otherwise return false, okay? This is a Tagless-Final program. This is implemented as a generic method, okay? This is an ad hoc polymorphic method, because representation can be whatever thing. It has to be something for which we have an instance of the expression type constructor class, which is our language, okay? But let's say that we want to create this Tagless-Final program from the expression that we have in some file. Okay, so what we have in our file is something like this. 1 is greater to 2, then return true, else return false. This is what we have in our file. And what we want is to parse this program and create something like the program that we have there, okay? Of course, what we can do is something like this. Okay, this parse program, which will be the signature. We receive a string, and then there could be parse errors. Okay, the program could be malformed, okay? And in that case, we will return some exception, a throwable. But if it is okay, we have to return our Tagless-Final program. And our Tagless-Final program was declared as a polymorphic method, but this is, of course, is not legal syntax in Scala. Okay? What do? Well, what we can do is to, instead of returning this program, a value of representing the Tagless-Final program, what we could do is to use an interpretation for our arithmetic expressions, for our language, in such a way that what will be returned from the deserialization, from the parsing, will be a value in this representation, in whichever ones, okay, we pass here. Which is the problem with this approach? The problem with this approach is that, okay, we will deserialize our program, but it will be deserialized for a particular interpretation. What if we need to evaluate our program again with a different interpretation? We had to reparse, okay, the program with this new interpretation. And what we might need, okay, is to run several times our program. And this happened to us in a project, okay? And still we need a type. We need a type that represents, whose values represent the different Tagless-Final program. How can we define this type? Well, the trick is actually very simple. It is exactly what we do for representing functions as values. When we have functions in Scala, the prime representation is as methods. Okay? This is how a behavior in an object-oriented language like Scala are represented. What if we want a value for representing functions? What we do, the trick is defining a function, one class, another class, whose only members are this method function. Okay? So in such a way that what we have, when we have an instance of the function one class, what we have is basically this method. We will do the same, okay, for our in our problem. What we have is this polymorphic method, okay? And what we will do is to define a new expression program, trait, abstract class, whose only method will be the polymorphic method that implements the Tagless-Final. Okay? The X program, which we have in the X program, simply an abstract applied method that we will return a representation in given a particular interpretation of our language. Okay? If we have an instance of this value, it's because we can implement this method. And if we can implement this method, what we have is a combination of the different combinators of the different constructors that we find in the expression type class. Okay? So what we have is a program. Okay? In such a way that the deserialized signature will be something like this. Not exactly like this if we are deserializing a typed program, okay? Because if we are deserializing a typed program, what we need is information as well, typically, of the type that we deserialize, the type of the program that we deserialize, but more or less it's this one. And there are sometimes in which this is not necessary, but there are sometimes, especially if you want to deserialize your program multiple times, and this may happen, then this is needed. And in typed deserialization, we found that this was necessary. Okay? Finally, last question. Where should I use Tagless-Final? Because this seems somewhat complicated, okay? Because this requires some experience and some practice, okay? But it is not always necessary to use this. For instance, I will tell a story about this project that was initiated by Alfonso Roa, one of my colleagues. This is Doric. Doric is a lightweight of applying a static layer on top of the data frame column expressions in Spark. Okay? In such a way that if we have this with plain data frame columns, we will have this expression. Okay? What we are selecting there is a multiplication of, we refer to the value column, and then we multiply this this column, which refers to integers, okay, in this particular data frame. We are multiplying these integer values with a Boolean value. This doesn't make sense, and the problem is that this will return an exception at runtime. Okay? At runtime, when we execute the data frame and do a collect or some whatever, there will things blow up. Okay? This error is generated at runtime. While using Doric, what we will find is an error at compile time. So, how Tagless-Finals fit into this project? When Alfonso first told me about this idea of Doric, I got very excited, and this is a particular interpretation for general expressions in a Tagless-Final defined language. And Alfonso said to me, keep it simple, stupid. Why? Because the only interpretation that is relevant for this project is the one for column expressions. We do not want to write general expressions in such a way that they can be interpreted as column expressions or whatever other data structure for Apache Flink or whatever. No, what we want is to work with column expressions. Okay? But still, what we found very useful is from our Tagless-Final experience is that in order to design the type of Doric columns, okay, what we did is something very similar to what we do when working out a new interpreter for a general expression languages. Okay, so we started with this Doric column, okay, which basically simply adds a typed wrapper for untyped columns, okay, and then Alfonso said, okay, but we want to take advantage of this typing in such a way that when we refer to a column in our data frame that it has the wrong type, or it has a different type to the one that we declare, we want an error at compile time of the data frame construction, okay? So what we did in this case, okay, these columns refers to the data frame. This is the same as when we have variables in expressions, in general expressions, and they refer to the environment. So the environment here is the data frame. And then what we want are multiple errors. Okay, so what we did is to just validate it. And this is more or less the implementation of the Doric column. Okay, it is somewhat more complex, but basically what we have here is this. And this is something that is very common while doing Tagless-Final. Okay? So, in conclusion, is Tagless-Final the same as the MTL style? In my humble opinion, no. Why? Because when we are designing a DSL using Tagless-Final, we are designing a full-blown DSL with the syntax and type system, semantics, standard and non-standard, and so forth. And moreover, the functions and the resulting language is more declarative. Being more declarative means that we can implement more interpreters. We can do asset interpretation, we can do normalization and so forth. And this is something that we can do with the monad tech class, okay? Bottom up or top down, the important thing is that the normalization is performed del tirón, okay? In one shot. And there are sometimes that it is necessary to do it bottom up, annotate bottom up, and there are other times that it is more convenient, depending on the problem, to go to annotate top down. Okay? What about the type of Tagless-Final program? Well, this is the this type that we didn't mention, but the type of our expressions, Tagless-Final programs for our expression tech class, is very related to the charge encoding. This is the Boehm-Verduch encoding, which is a type of version of the charge encoding. Okay? This can be useful in type of deserialization. At least we find that. Okay? There might be other contexts in which it is useful as well. When should I use Tagless-Final? At least Tagless-Final using type constructor classes. Well, when you need multiple interpretations, when you need very different interpretations, in those cases, the cost of designing all this language might be useful, type constructor classes and so forth. Okay, but sometimes this is over-engineering. Okay? And we functional programmers have to avoid over-engineering. Question?
So you mentioned that we shouldn't be using tagless finals really when we don't have more than one interpretation.
Yeah.
So in that case, what would you recommend?
Well, Tagless-Final can also be said that we are doing Tagless-Final when we are working out a DSL for a particular interpretation. Right. It is only that these Tagless-Final representation that do not use type constructor classes, okay?
Yeah, I guess I'm talking about, for example, when you're going to write a new application and you don't really have the need for multiple interpreters, right? There's multiple styles in which people will write in Scala. One might be tagless finals, full-on polymorphism, F plus the type classes. That's one way, right? The other is, well, my application is very concrete. I'm not going to need multiple interpreters, so I'm just going to use I/O or even not I/O if the kind of effects that you care about are not really, or you can do them in the environment or whatever. Yeah. So for the general purpose, when someone is writing an application, would you recommend using tagless finals or would you recommend some other approach?
I would recommend to stick to the most simple approach that it is valid for that case. Okay. This kind of defensive approach, no, I will do or generalize and with type constructor classes or using the monad tech classes you are using, because this is something that also applies to the MTL style, okay? Right. This is something that had to be done with care because you need a team which is very competent. The code can get very, very complicated. And well, sometimes you will find many errors and problems using the implicits and ambiguity and this kind of. So I think that if the team is experienced, okay, then well, it could be done. But if you have a team which is not very experienced, maybe it is not worth the effort. Okay, but concerning Tagless-Final, if you are working for a particular project in which a DSL can be identified very clearly, then a Tagless-Final approach would be nice. And maybe the best method is starting with a very soft representation based in one particular interpretation. And if you find need for different interpretation, then you can abstract away and define the type constructor class. Okay? But you can do Tagless-Final without type classes. Okay? I think that in the papers from Lekis-Eliov, they introduced the Tagless-Final approach using final interpretations, so-called final interpretations without concrete interpretation. It is only then, when you find all the similarities between these interpretations, that you abstract away all the difference and define all the common factor in a single type constructor class or type class. Okay. So references. The site, the FTP site from Lekis-Eliov is full of information about Tagless-Final, not only Tagless-Final continuations and so forth. This is a incredible source of information. Then what you will find also in our GitHub is this Tagless-Final tutorial, in which you will find embedded with a lot of detail this optimizer, this normalized representation for relational query language. Okay. Then in this also this other report GIS, you will find also some examples about the charge encoding. Okay. In this project Lambdas, in this repository, you will find a lot of crazy stuff about the Tagless-Final, implementations of records in the Tagless-Final style, helpers to do typed deserialization, and so forth. And in this other repository typed, you will also find some examples of typed deserialization, what you need in order to do typed deserialization, although with an initial using algebraic data types, not the Tagless-Final style. Okay, so long live Lambda World Meetups, okay? And thank you very much. And see each other in the Scala Meetup of Madrid, okay, whenever you want. And thank you very much.
Thank you, Juanma. Is there any question over here? Over here. We have also questions in the streaming. So we are gonna have this question, and afterward we are going to put the streaming question in a slide in order to have them both.
Okay. So first of all, thank you for the talk. It was quite interesting.
Thank you very much.
And I wanted to ask you, coming from, in your case, not only from the industry sector, but also from the academic sector, do you think that these, let's say, techniques, patterns, or whatever we want to call Tagless-Final, should be taught at the university, or are they? Because I found that most of the time, this is something that relies on the companies, and we have to train the people when it comes to us. And I don't know, maybe it is worth to teach these things to the people, not in a very complex way, but...
The problem is that there is no time in the study plan, okay, of the typical undergraduate course. There is a subject on functional programming. Okay, and this is normally half of a semester. It is not the whole semester. It is only half. Yeah. And what you can do in that very short period of time is explaining algebra data types, the carry algorithm of it, okay, and higher order functions, but no more. No type classes, for instance. No type classes. Yeah. No type constructor classes, no type classes, okay? And also no applications, okay? It is only in this very short period of time, what you can do is to teach something very formally, but not with an application. For instance, let's implement a Wordle game. For instance, you can't. There's no time. Okay? So maybe in a master class, okay, then a master course, then you might find time, okay, for teaching this kind of stuff. It fits really well with a course, for instance, in which you teach formal methods or techniques for implementing embedded domain-specific language. It could be done there, okay? But there are not so many master courses in which you can teach. There is a master course in Madrid, which is run by the Polytechnic and the Autónoma and the Complutense, which is a master in formal methods, where maybe there are subjects in that master in which this topic fits, okay? But I'm not sure if they do that, okay?
So any other question here? No? So let's say, if you don't mind, you can talk, you can speak out loud about the question that we are going to read.
Oh, okay. There's a quotational quill. Well, yeah, this is. Okay. Could you elaborate on pros and cons of this approach for DSLs versus quotations at a quill? Thanks. Thanks for the question. This is very interesting. There are different approaches for implementing embedded DSLs. Tagless-Final is one of them. Then you could use algebra data types as well, and then you could use so-called quoted DSLs. And quoted DSLs are more or less based on macros. Okay? And this approach, for instance, is the one that is followed with quill. Okay? And this is very nice, the quill approach. Why? Because you do not have to create a new syntax from scratch. If you need a syntax for comprehensions, you already have the syntax for comprehensions in the Scala compiler, in the Scala IST. So you reuse this syntax. And programmers, we will use native Scala syntax for writing these queries. We can also write our comprehension queries using Quell, using for comprehensions, you saw. But this is only with a lot of effort in order to simulate the flat map and the width filter and the map methods that are required to translate for comprehensions. Okay? So this is overhead. And if you are using the host language AST, this is more easy. Which is the cons? The cons is in the case of quoted DSLs is that okay, you have to deal with the AST of a very, very, very complex language. And this is normally not very well modularized. If I would have the expressions AST of Scala in this single place, and I can reuse simply that, okay, then it might be useful. But when I borrow all the Scala AST, I will have plenty of things that maybe in our language is not needed. So you have to write defensive programming and get rid of many different parts. Okay, so I mean, I lean towards quoted DSLs lately, but this is also have problems. Okay.
So I do think that we are almost done.
Yeah.
Thank you so much again for coming, Juanma. Incredible.
Thank you.
Are you gonna dance? Are you gonna dance? No? So, thank you to everyone for coming. Thank you for the people that are watching online. Thank you for the people that is watching the recording. And this is the first try. This is the first meetup. But we will come back and yeah, let's do more Lambda World. Thank you so much.
Thank you.